Okay, let us get back to the L squared integrable functions. So L squared functions, say psi of x of t, must go to 0 as x goes to infinity very rapidly, right? Otherwise, the norm will not converge. In fact, I think we also assume that this goes to 0 as x goes to infinity. So this allows us to make the statement that if you fix the norm, if you measure the norm, okay, the norm of an L2 function is, okay, the norm of an L2 function, which solves, I should say, that solves the Schrodinger equation has a fixed, okay, so the norm of the norm is constant in time in the absence of a source or a sink. A source is something that creates particles, and a sink is something that absorbs particle. Okay. So if you don't have any source or sink, then once we calculate the norm of a wave function that is the solution to the Schrodinger equation, is going to be constant. And it's pretty easy to prove, and let's do that. So let us take the time derivative of the norm. So what is the norm? The norm is the integral over all space. Let's just call that v, d cubed of x, psi star of psi. Now this thing only depends on time, right? Because the spatial part has been taken out by integrating it over all space. So we can write this integral as the derivative as a partial derivative. So then we can take the partial derivative inside, and then we will have, by Leibniz rule, two terms. Now what we can do is that we can apply the Schrodinger equation here and the complex conjugate of the Schrodinger equation here. So if I do this, then I get one over minus I h bar. For the first term, we get minus h squared by 2m Laplacian acting on psi star times psi plus, because there's a minus sign outside, No, because, yeah. Sorry, not because of that. Just the complex conjugate of the Schrodinger equation gives us that. Plus V of psi star psi. And then from the second term, we have plus h squared by 2m Laplacian of psi times psi star minus V psi star psi. And so we see that the potential terms drop out because the potential function is assumed to be real. So now what we can do is that we can factor out so we can take the I upstairs and we can factor out all these constants and then factor out the gradient operator, sorry, the divergence operator. And then we have, I think this is known as Green's identity or something related to that, yeah. So when this guy acts on this thing, we get 4 terms, but 2 of these terms where this thing acts on this and this thing acts on this, those things cancel out because of the minus sign. And what we have left is this guy and this guy with a sign difference. So this thing is a vector S, well, times this. Then we can write this as d cubed of x, the divergence of S, integrated over all space, which we are calling V. Now we can use, so this is dN by dt. So we have used Schrodinger equation to turn the right-hand side to a spatial derivative. Now we can use Gauss's divergence theorem to turn this volume integral into a surface integral, say d squared of S, the surface integral, and it'll be over the boundary of the volume of all the boundary of all space, which is a huge 2-sphere. And the integrand is going to be a unit vector times S, right? So pictorially, we have, this is like the inside of the circle is all of space. Well, it's a sphere. And this is the boundary. The yellow circle is the boundary. It's a sphere. And n is, at every point, n is a unit vector pointing outwards. Okay. And we are taking the dot product between n and this current S. Now, what is this current? This current S is proportional to psi star gradient of psi minus psi gradient of psi star. But we know that as x goes to infinity, psi goes to 0 rapidly. Otherwise, we would not have an integrable L2 integrable function. So that means that for this choice of the volume, this is 0. Because S is 0. And therefore, the norm of the wave function is constant in time. Okay? So once we normalize our wave function, which is L2 integrable, it will be preserved. Its normalization is going to be preserved. Okay, any questions?
I didn't understand the norm thing and L2 integrable yet.
Well, then I think you should go back and read watch the lecture more carefully and read the notes again, because I mean, if you have a more focused question, I can answer that. I mean, you probably mean this. You understand the definition, but you don't have a gut feeling about it.
Yes.
Yeah, so that'll come with time. What I'm trying to say is that, roughly speaking, let me give you an example of an L2 function. Let me give you an example in one dimension. Do you know the Gaussian?
Yes.
Yeah, the Gaussian is an example of an L2 function. So you have e to the minus.
It will diverge when x goes to infinity.
Well, it doesn't diverge. It converges to a value, right?
Oh, I mean converge.
Yeah. So if this is psi, then you know that psi star of psi. So you can add to it a phase. Okay. I don't know, something like this. That phase will drop out of this, right? So this is going to be e to the power. So let's put a half here. Then it will be e to the power minus a x squared. And then if you integrate this from minus infinity to plus infinity, it's going to give you pi over a or something like this, right? And this is the norm.
So the norm is the answer, not the projection of the vector to a lower plane.
Yeah, it's not a projection of the vector to a lower plane or anything, no.
Oh,
okay. The norm is the length. The word norm in mathematics means it's a length.
Oh,
so this is a kind of a length, right?
I have a question.
Yeah.
While working out, you said we can cancel them out, the potential terms, because they're assumed to be real. Could you elaborate on that?
Oh yeah. Basically, yeah. I mean, so going from here to here, I skipped a step, right?
Okay.
And so this gives you this guy, which is the Schrodinger equation. This is equal to, there are factors of I, of course. But when you go from the complex conjugate of here to here, yeah, let me just, this is something which is actually going to be my next thing. So let me just discuss that, okay?
All right.
Just hang on 1 second, yeah.
Oh, I think if V is not real, then taking the complex conjugation would make V star. So we can't cancel.
Yeah. If V was not real, then we would actually have V star here, and therefore these two terms would not cancel. Yeah, that's it. Thank you, Dan. So I actually left out this step on purpose so that you guys are able to work this out for yourself. It's a trivial one step, but